So, ladies and gentlemen, welcome to the 5th talk in the Geology lecture series this year, and it should be a fantastic one. Before we get to that background, if you have not on your way in signed one of these handy-dandy little sheets, at the very least with your name and the city where you live, I'd appreciate if you take a couple seconds on the way out to go ahead and do that. Also, I'd like to point out that on May 18th, only basically 3 weeks away, the 6th and final talk in the lecture series this year is going to be here. It's going to be Dr. Brandon Dugan from Rice University, and he comes to us from the ocean drilling program. And so one of the sidebars there, if we've got already 15 people signed up, we've got room for 24 teachers in a workshop during the day. So if you happen to know anybody that teaches science that might have fallen through the cracks, we do have some space. They can feel free to contact me if they're interested in finding out a little bit more about how to bring ocean drilling in the deep ocean into their science classrooms. So that should be a good conclusion. And I have just finished talking to Craig Young at OIMB, and so if you are looking for next fall, go to www.socc.edu, find Metzger or Geology, and find the Geology lecture series. At some point in the not too distant future, that will be on. We've got Deborah Kelly from the University of Washington, one of the also leading deep sea researchers that's going to be coming to talk about hydrothermal vents on kind of a nice co-sponsored bill dealing with the OIMB public lecture next fall, as well as the Geology lecture series. So it's somebody that's been on my list for quite a while, and she's done a lot of work with Craig Young, so it should be a good talk on either October 11th or 12th. We haven't quite figured that one out yet. So sitting around and wandering around with the Fisher family today, it was kind of interesting. We found out that part of our worlds kind of overlap with a little stint in Rochester, New York, me growing up and Dan being on the faculty at the U of R, and his wife working and going to school at the U of R as well, which is always intriguing. Dan got his bachelor's and PhD at Harvard University, and one of the early comments that I had from him involved, if you stay with us, we have an indoor cat. And the response was that it's not so bad, but I do have a cat allergy that I believe was generated by lions. And I thought to myself, okay, first, please don't bring a lion with you. Okay, you're allergic to them, so that's good. But while we were driving around to Shore Acres and around town today, it's like, okay, so you got to tell me, the lion allergy causing cats, what's the deal with that? And at Harvard, some of what he did and some of the research going on there involved basically morphology and movement and a variety of different things, and bringing live lions to different places where Dan worked, which is intriguing, and climbing through where the lions escape. So that's more story than you all want. So and seeing that most people are getting in here now. How many of you have seen Dan on some form of National Geographic something or other? Okay, I expected a few more. Anyway, this talk came about from one of the many ways that I find people to come and speak in Coos Bay. Frequently, it's the people that come here asking them who has good stories in science and who gives a good general audience talk. The other way for this one initially was me sitting home after a music festival concert, not being able to fall asleep, and channel surfing. And usually I don't stop on geology, but this time I did. And it's like, wow, that's a cool story. That would be good. And so all of that results in Dan being here. Dan's at the University of Michigan, go blue. And just coincidentally, a nice lady brought me a mastodon tooth that she found at Devil's Kitchen some time ago for our teaching collection here. And of course, I passed it off to Dan because I deal with little teeth at some point in my past. And he said, yeah, it's a lower tooth, it's a molar, it's an M3, and the animal probably died in its early to late 20s. And there's probably more, but I'll find that out a little bit later on as well. So it's my pleasure this evening to introduce to you Dr. Daniel Fisher, New Insights in the Lives of Mammoth.
Well, thank you very much, Ron. It's my pleasure to be here. For one thing, I guess Ron didn't mention this, I'm returning to the state of my birth. For another, I've, well, thank you. The word on your lecture series is spread far and wide. I hear there are a lot of great people that come talk here, and I hope I can slide in and hold up my end of the bargain. But it sounds like you have a really interesting program with great longevity here. The other thing that makes this nice is I get to come and talk about mammoths. I've just gotten to be really completely entranced by these animals. I started out in the field of paleontology studying horseshoe crabs. And I thought horseshoe crabs were wonderful, and they are. But along about, I guess it was too early to call it mid-career, it was soon after I moved to Michigan, actually, I started working at some mammoth sites and mastodon sites, initially to really just help some of my colleagues. But the problems that presented themselves as we studied some of these animals were so intriguing that they really captivated my sense of mission, commitment to various research projects, and before long, they'd basically taken over my research career. Now, I've already let one little piece of new information out of the bag, and that is that I slipped there and mentioned mastodons. And I will be explaining what those animals are. They're relatives of mammoths. Both of those are relatives of elephants. But I hope in a minute to clear up any uncertainties there may be in the room at large here about what we're talking about. The other thing that I want to make clear here before we move off this opening slide is that we are going to be focusing on some new insights. Now, I don't want to claim any great accomplishment for these new insights, though in fact many of them have emerged from the work that I'm doing. What it really is that I've had the great privilege to work on some amazing specimens with collaborators that are themselves generous and resourceful people. There's been more than a decade of adventures in Siberia and elsewhere that have gone into these studies. And so it's really just the flowering, the emergence of the sort of intersection of many different ideas and observations that have brought about these insights. But the short of it is we are learning a great deal about these animals. We can almost bring them alive, not in the sense that the geneticists would like to claim they'll do in 2 or 5 more years. We can address that in questions if you want, but it's not really the subject of my talk. I mean that we can peer into the lives of these animals in a level of detail that you'd hardly imagine you could do for your grandfather or grandmother. And yet we're able to look at the lives of these animals that lived tens of thousands of years ago, and you'll see the kinds of things that we can learn about them. Now, this particular image is an artist's reconstruction, of course. You can tell that. It's associated with a major exhibition that I helped develop by working with the Field Museum in Chicago. That exhibition is now touring. But, you know, and there are things that we could pick at, I suppose, in the reconstruction, but I think it gives you at least a sense of what these animals were like. Clearly, their relationship to elephants will not be lost on anyone. But these are elephants, if you will, that lived at the top of the world, that lived in the high Arctic, and they're shown here somewhere in Siberia on land that's very much like what you would now see as tundra, but it's different in the sense that it's got more in the way of grassy vegetation. It's a land, an environment type called the Mammoth Steppe, after its most notable occupant, the mammoths. Let me move on here and introduce the other animals that we'll be spending time with. Here on the left are our same mammoths, maybe a different part of the family. You'll note a little calf right here, and I'll come back to talking about a mammoth calf. So these are woolly mammoths. I'm not sure my laser pointer can be seen up there, but woolly mammoths that actually lived across the whole stretch of northern Eurasia and into North America. We also will be looking at mastodons here, and I'll tell you a little bit more about them in a moment. Those, for most of the Ice Age, were living only in North America. And then down here on the lower right, we have African elephants, and indeed we'll be talking about modern-day elephants too. They are an interesting point of comparison for our understanding of all of these animals. But I want to emphasize that when I talk to you about the biology of mammoths or mastodons for that matter, it's largely on the basis of evidence that we can find in the fossil remains of those animals. It's not just that we're making comparisons with elephants. You know, well, elephants do it this way. I suppose mammoths or mastodons did it that way. No, we, in many cases, in most cases, have direct evidence of what mammoths and mastodons were doing. Now, before going further, I want to put this in a little bit of historical context. This is a sort of family tree, the evolutionary history of so-called proboscideans, animals, mammals with trunks and tusks. These are the relatives of elephants, mammoths, mastodons. And this first tracing is showing you mastodons coming from the first proboscideans back here in the Eocene, 50 million years ago and more. This is then the lineage that goes to the modern African elephants, to Asian elephants here, and you can see that the ancestor that those groups share with one another is all the way back here, more than 30 million years ago. Mammoths, however, split off from the lineage of elephants here, and so they're actually much closer relatives of modern elephants and much more similar in many aspects of their anatomy, behavior, and biology. We're going to look now at geography, and I'm not going to give you the whole detailed story, but basically all of these animals started in Africa, and some of the early ones spread out of Africa. Some of the early ancestors of mastodons, they then moved on into North America. Meanwhile, there was a sort of flowering or radiation of other elephants and early mammoths that spread to different parts of Africa. We had the move of what we now call Asian elephants out of Africa and into parts of southern Asia. They later went extinct in Africa, which is why the name Asian elephants applies. We had then the first mammoth coming out of Africa and spreading across high latitude regions of Eurasia. Eventually, well, here it's syncopated with the move of some of the early mastodon relatives into South America, then mammoths moving into North America as far south as Costa Rica, and then finally woolly mammoths coming into North America at the very end of the Ice Age. You don't have to remember any of that. All you have to know is that it's a really complex history of movement out of Africa and spreading across much of the rest of the world. And whereas today we have only about 3 lineages, 3 species of elephants, 2 in Africa and 1 in South Asia, back in the Ice Age we had more like 15 or 20 kinds of elephants occupying different parts of the world. So it was a really different phase of their history. Now, we're going to focus for a while on Siberia. Siberia is where I do a lot of my field work and where some of these spectacular specimens that I'll introduce you to soon have been found. And one of the first of these is the Yulagir mammoth, and that's where it was found. I'll show you a picture of it in just a moment. The next on our list is going to be the Oymyakon mammoth, and it was found a little further to the south, the only one of these that was found south of the Arctic Circle. This then is Luba, a mammoth calf that is almost looks alive. It's so well preserved. Next came Chroma, not quite as well preserved in some respects, but better in others. Then Yucca, and most recently Xenia. And we'll now look, so these really come from across this northern tier of Asia. I should say, maybe just for setting the stage, that Russia's boundaries are outlined here. It's a huge country, spreads across 11 time zones. Most of the animals that we're talking about are the Asian part of Russia, which is Siberia, which is basically to the east of the Ural Mountains here that separate European Russia from the Asian portion of Russia. But all across here, we've done work and have amazing material. All right, this is the Yulagir mammoth. This was its head. It may not look like it's going to win any beauty pageants or anything like that, but for a mammoth, it's pretty darn good. Here is one of its limbs. That's the sole of its foot. If you know elephant feet, that's basically like an elephant foot looks, that sort of cracked, rough sole of the foot. And here you can see fur on its sort of fetlock area. But then the flesh is decomposed up here higher on the limb. There's a shoulder blade up here. So large parts of the body were preserved. This is a tusk. We're going to be returning to tusks and finding that a lot of this information on the lives of these animals is going to come out of tusks. So that's a bit of a hint of stuff to come. This is Oymyakon. When we found this, we really rejoiced that we had this much of a mammoth. Okay, it's only head and neck and shoulders, but look here at its ear, so well preserved. There's a little musk gland, a temporal gland that's here on its face, its eye, its little trunk. Inside the bones of its face here was a single little starting of a permanent tusk with a line on it that marked the part of the tusk that was formed before birth and the part that was formed after. So that was an indication, a bit of history of the animal, an indication of the time it was born. And we were able to figure things out about the early stages of life from that. In a way, it seemed, how could we be so lucky as this? But the next animal that we found was Luba. This is the animal that I think Ron saw on the documentary. And the National Geographic documentary recounting the tale of this animal is called Waking the Baby Mammoth. And it really looks as if she's just about to be woken up, just about to walk forward and snuggle this little Nenets boy. The Nenets people live on the Yamal Peninsula in northwestern Siberia, and it was a Nenets family of reindeer herders who found Luba. And in a moment I'll introduce you to them. But you can see just how special this specimen was. In this photo you can't see it, but although she lost most of her hair, some of her hair remains, all of her soft tissues remain, and her internal organs. And we were able to do a lot of work then on her anatomy, her diet, and so forth. This is Chroma. It turns out Chroma at death was a little older than Luba. Luba was only a month old. Chroma was about 2 months old, and Chroma was correspondingly larger, more well developed. Not quite as well preserved in the midsection here, and Chroma's there's a better angle on Chroma's head and face region. Unfortunately, Chroma's tusk was eaten by ravens after she was found. They found her and then went to go get more people to collect her. When they came back, the ravens had already dove in and fresh meat, dinner time. So too bad. But they weren't able to rob Chroma of her nice smile there. So there was still, and Chroma's soft tissues were actually better preserved than Luba's through an interesting turn of events that I probably won't have time in the main talk to go into. But here again, the soles of her feet, the hair on her legs, you get the sense that these animals are, yes, somewhat degraded, and yet there's so much there, so much to be learned about them. This one is one of the most recent. This is Yucca. This is a young mammoth that was found up on the shore of the Arctic Ocean. Obviously, there's some folks here for scale. This is a larger animal than either Chroma or Luba. And in parts here, in the leg region, it's dramatically well preserved. Look at that fur, this sort of strawberry blonde fur. This was also called by some people the ginger mammoth. It turns out that although we have the skin of the upper portion of the body, most of the skeleton and the organs had been removed. It's part of the mystery of this animal as to just exactly when and how and why. But by looking at the preserved skin just as it is, we find things like claw marks of ancient steppe lions. And it seems that this animal was pursued close to the time of its death by lions. It also has a broken leg. And so the lions seem poised in our imaginations to finish it off and devour it. And yet there is no mark of the usual killing bites of a lion. And there's some other indications that perhaps ancient humans were involved. And so we've at least speculated that they may have scared off the lions and begun to butcher and process and take advantage of parts of Yucca's body. But that's a big question that I'll have to leave probably right there. This is the most recent of these mammoth finds that I'll mention. This is Xenia. It's a considerably larger animal, not so well preserved on the top. You see here ribs coming out, but the undersurface of it is frozen in the sediment there. And so it's basically as if you divided it down the middle, and half of it is great, and half of it is not so great. But the specimen has still a lot to tell us. It does have a tusk preserved, so returning to our theme of tusks, we will be able to learn a lot about the life of this animal when we're able to analyze that tusk. Now, that's our quick survey of some of the remarkably preserved animals that we're dealing with. I mentioned that we also gain a lot from our association with people. Of course, this includes my Russian colleagues, colleagues from some other countries as well, but even the indigenous peoples of the North have a lot to offer. In some cases, of course, it's that they're the ones on the landscape who find these specimens. So it's thanks to them that the specimens are reported. But in addition to that, going up there, living with them even for a time, talking with them, teaches us a great deal about life in the far north and what both human and animals would have had to experience, would have had to have faced for life during the middle of the Ice Age at these high latitudes. And I have to say a great deal of our insights into even the physiology and certainly the behavior of mammoths has come from sort of putting two and two together, things that we've learned from these people, things that we've observed being up there, all that together with things that we've learned about the specimens. This is a little more close-up view of that family and their caravan. They're moving their camp as they have to do about every 5 days as they follow their reindeer herds on an annual cycle that may be as much as sometimes close to 1,000 kilometers. The herd itself is much larger than what you've seen by a factor of maybe 20, but these are simply the animals that are tame enough to pull the sleds that hold all of their worldly possessions, all of which fit into this one teepee-like tent called a chum. Its walls are made of a double thickness of reindeer hide over poles, and that's their home. That's their home throughout the year. In the middle of winter, it'll be 60, 70 degrees centigrade below zero. Howling winds sometimes. Somebody has to go out and run the circuit and watch the reindeer throughout the dark polar night. Remember, no sunlight at any time during the 24-hour cycle. There are wolves about threatening that reindeer herd. And so it's a pretty hard life up there. And if you think about early human colonization of the North, they would have had to deal with all these problems, no matter what lifestyle they had. It probably wasn't herding reindeer, obviously, in the very earliest stages. But there's a lot we have to learn about human history and the early colonization of the North. I'm going to switch now. I'll keep watching my clock, and that's going to be my enemy throughout the evening here. There is so much to talk about. The most difficult thing in preparing a talk like this is to try to weed out. And so I'll keep chiding myself, flogging myself to move on. So we're now going to move on from the Nenets people to one other indigenous group of the north. These are the Yulagir. The Yulagir are a group of which there may only remain about 200 people alive today. The Yulagir language is then spoken by not even all of those. Some of the young people haven't fully learned Yulagir. They're transitioning to learning Russian, speaking Russian, or Yakut, which is one of the other indigenous languages of northern Yakutia. Many of these people during the summer, when they aren't fishing or hunting, are off nowadays hunting for tusks. And the reason is that there is a commercial trade in ivory in the far north. It's a sort of, some people refer to it as white gold. The most favorable light, I guess, in which I can paint this is that some have expressed the sort of optimistically the hope that hunting mammoth ivory and trading in that might, to supply the sort of commercial demands in China and Japan, might relieve some of the poaching pressure on modern elephants. If it would, I would be one of the biggest supporters. The problem is that it simply feeds the market, and the poaching on elephants continues, and the commercial trade in mammoth ivory is not the solution that it might seem to be. In any case, it is the short-term answer to liquidity, answer to cash income for many of these peoples that have next to nothing except the land around them to live off of. And so there are strong economic forces at work that send them for a portion of the year to commit their lives and sometimes risk their lives to bring back these tusks. They find them along the sea cliffs, use small boats such as you see anchored just offshore here to bring them to a central gathering place. Here, hike them ashore. It may look like an easy job, but each of those weighs probably more than 100 pounds, something like 140 pounds. They're incredible specimens. Some of you, if you take National Geographic, there was an article in, I think, the April issue that included pictures by the same photographer. Most of the pictures you'll see tonight are my own, but I've indicated where someone else took a few, and this is Evgenia Arburgeva, and she grew up in this village of Yulagir and has some amazing photos in National Geographic, and these are some copies of some of her photos that you're seeing right here. Incredible specimens. It's an incredible landscape, and again, much to gain from studying it. One of the reasons that we were so interested in these Yulagir people and their territory was it wasn't only the big tusks that they had found. Most of those, for better or worse, were destined for this commercial market and not going to be available to us to study for scientific purposes. But we knew of a site where they had found abundant mammoth remains outcropping along the shore of a river. And what they've done is blasted into the permafrost with hydraulic hoses, basically fire hoses on diesel pumps. And they've blasted these tunnels that go back into the permafrost. This is a person in a raincoat, and these are mammoth bones jutting out of the wall of this tunnel that's been blasted in. This is frozen permafrost surfaces right here, a little bit of fog on the lens, but again, mammoth bones coming out of the walls of this tunnel. And this is a map view of this tunnel going back here, following the vein of bones, as it were. They're like miners mining mammoth bones. The mammoth bones, it turns out, are concentrated along what was a little channel, a little waterway, a little stream bed back on the landscape in the time 30,000 years ago when some of the first humans who had come to inhabit these northern regions were living here, camping, having their home sites. And it seems, as best we can tell, that they were hunting mammoths, woolly rhinos, horses, musk oxen, steppe bison, and certainly using the meat for food, but also storing the bones in these channels, basically to keep the bone in a fresh condition so that they could work it, so that they could come back to it and use the bone and ivory for tools. That seems to be the explanation for this concentration of material. The blue is the cross-cutting ice wedges that have formed afterwards. And these tunnels are in some cases barely big enough to wriggle into. And as you might imagine, there's some danger of collapse of those tunnels. And I don't need to tell you what would happen if they did collapse. But out of these concentrations, they've been pulling enormous numbers of bones and tusks. It's just an incredible mass of material. And what we were interested in is the material that the commercial ivory hunters were leaving behind that would nevertheless tell us about the lives of these people. And to get up there and have the chance to work at this, we were willing to make a considerable investment and take a certain number of risks ourselves. Here's a group of 4 students that I brought with me last August and September. We're on the coast of the Laptev Sea, the local sort of embayment of the Arctic Ocean. It's 1 a.m. That's as far as the sun sets at that time of year. It would set much less than that in late June or July. The vehicle that my students are standing in front of is called a Visdihot. And a Visdihot is basically a tank with no gun or turret. It's a fully tracked vehicle. It's actually illegal on the tundra because it'll tear up the tundra. But the ivory hunters basically flaunt that and drive here and there wherever they need to, into the ocean, across rivers, through swamps. And that's how we made it for hundreds of kilometers across the tundra, exploring the vast landscape and finding in the course of this many tusks, many bones. The deal was basically they would take the tusks, we got to keep the teeth. And it turns out that a lot of the record, a lot of the information we're interested in is preserved in the teeth as well as in the tusks. Not quite so well, but well enough. We lived on the tundra basically, camped out. This is a somewhat larger Visdihot basically keeps more people and gear and so forth in there. We're sitting around the campfire here. Again, it's midnight, long days, hard work. You might ask, what's for stew? Well, that night it was loon stew. I don't know how many of you have eaten loon, but they're pretty tough birds, let me tell you. This may take you a moment of looking at it to see just what it is. This is the snout of an animal. There are its front teeth. There are some curved horns. This is what I call the zombie bison. And here's a slightly better view. It's against a white sheet here. And you see that it hasn't even lost its grin. It's got flared nostrils. Every bit of its skin is intact. Its hooves, its entire body, all its internal organs. It's only lost some of its fur. So again, spectacular preservation, and a lot to be learned about the biology of this animal from dissecting it and studying it, which we hope to do in the next year or so. The next to the last site that I'm going to introduce you to is this one, this is an aerial view of the locality, a locality near the village of Batagai in northern Yakutia, which is basically central eastern Siberia. And it's clearly some depression. The locals call it, in reference to this outline, the tadpole, but it's actually a huge crater-like depression. And what it is that about 15 years ago, the local town decided to dig a quarry. They thought they might be able to find sand that they would use for making cement and so forth. Well, there was no sand, so they abandoned the quarry. But the walls of this shallow excavation were then vertical. They They were constituted by the dark-colored sediments of the frozen sediments of the permafrost, these permanently frozen soils of the north. And as the Arctic sun in summer just goes round and round, remember it doesn't set, it goes a little higher in the south than in the north, but it just goes round and round, it serially irradiates all those walls, and they started melting back faster and faster. And this is the closest I've seen to something that I would call the catastrophic melting of the permafrost that some climate change scientists are beginning to talk about. Over the course of a decade or so, the walls of this constantly enlarging crater have come to be almost 100 meters high. And this interior is then filled with the remains of what has collapsed into the interior and not been totally swept away. This next view shows some of the sunlight glinting off the walls of this crater. The sort of pocketing is the sort of uneven melting back of the walls of ice and sediment. And constantly as you're there, this is in fact a fairly dangerous place to stand, constantly sediment is crashing down from above after melting. And so if you closed your eyes, it sounds like you're in a war zone. As mass of sediment after mass of sediment crashes down below. And the volumes of meltwater that are produced are just incredible. The surface basically can't accommodate them all. And so the meltwater excavates its own conduits into the frozen substrate, into the frozen sediment below. And as these meltwater streams, as big around as some tree trunk, go down into a conduit only maybe 20, 50% larger than them, there's this loud echoing, the landscape is just alive and threatening and seems like it's going to crash around you at any minute. But, so why do paleontologists go there? Well, this is why paleontologists go there. There are bodies coming out of this frozen permafrost. The commercial ivory hunters go there because those bodies include whole tusks sometimes. But this is the body of a steppe bison calf, probably just a few days old at the time it died. But it's all there. Little nubs of horns in its ears, its lips, everything is there. And again, a great deal to be learned about the lives of these animals. The last site that I'm going to show you, and it's just one slide here, is of Wrangel Island. Wrangel Island is a small island off the northeast coast of Siberia, and it is the place where the last mammoths lived. The last population of mammoths, which survived until about 3,700 years ago, lived here. 3,700 years ago is when the Egyptians were building pyramids. Lots of human history was already well underway, and we still had mammoths, and this is where they lived. And about now 2 years ago, I had the good fortune to be able to go to Wrangel Island, and we found in the course of about 2 weeks, we found, something like 55 mammoth tusks, and these are 4 of them. We had just spent the night in a small hut, crammed into a small hut, where we had to bar the doors behind us, and the doors and windows were spiked with long metal spikes to keep the polar bears from prying in and extracting those little delicacies that come out of sleeping bags. So you come out the door, and there the frost was on the ancient mammoth steppe, there to be eaten, but no mammoths more to eat it. There are muskoxen on Wrangel Island today, and again, there's a recent National Geographic article that shows some of those muskoxen. They're incredible animals, but just the landscape, the mist just blowing back there, the mountains with, this was in early September, mountains with snow on them, and the low morning sun shining on those mammoth tusks. I thought, this is the most beautiful place in all the world. Well, except for Oregon, but... All right, well, that's the end of our look at sites. And I've spent much too much time, so now I'm going to have to pay for it and move more quickly. So new ideas, yes, come from new specimens, new sites, from people. They also sometimes come from new technology, and you get a look at some of our new technology here. What I'm doing is laser scanning a mammoth skull. This is a mammoth skull. Mammoths are pretty big. I'm not that small. And what I'm holding in my hand here is not something out of Star Wars, but a laser scanner. It's not so different from a supermarket scanner. And with these little targets that are scattered all over the skull, it basically processes visual information and changes that into a 3D digital model of the skull of that animal. And we've done this with entire skeletons. And this is just to show you, we're still improving the pose and articulation of this, but this is a mastodon skeleton that's been completely scanned in 3D. And what do we do with such things? Well, just here's one example. This is an animation of an excavation. Now, everybody quick dig. Dig, 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 dig. Everybody. All right, good job. You've now exposed all the bones of the Hyde Park the Mastodon site. And what we're doing is basically going on a flyby, a sort of bird's eye view of how every bone at that site was positioned. So this is essentially an interactive model of the site as we found it. And with these 3D models, we can portray what was there, which, if you think of the sort of forensic angle on interpreting sites like that, much of that spatial distribution, that's evidence for what happened around and after the time of death of that animal. And so the sort of new standard for publishing on such sites is to make these 3D models like this. And we can now make those models, click on a bone, open up a 3D model that you can rotate on screen. I won't take the time to show you that, but it's really very useful for all of our understanding. Now, that's just one example of modern technology. There's also ancient technology that we have to understand. And what I'm showing you here is one bone from the hand of a mastodon, and you'll notice that there are some scratches or cut marks across it here. And in fact, we frequently find things like that. Here's the end of one of the long bones of the forearm of a mastodon, and at essentially a wrist joint are these grooves. Now, I won't take the time to walk you through all the arguments, but those grooves were produced, we're quite sure, by driving a wedge-like object into that wrist joint to help disarticulate the animal at that point. So these marks are evidence of human processing of the carcass. And from studying the preservational context in which these bones were found, we figured out, and again I'm shortcutting a long argument, that the reason the bones are preserved where they were in pond sediments is that people were butchering these carcasses and bringing carcass segments to the ponds, intentionally submerging them in those ponds, and the meat then would be stored there until it was needed. They could then come back and, even in the middle of winter, make a hole in the ice and fish out carcass parts for dinner. Well, you might say, well, maybe you would, but I wouldn't. But I decided I would. And I actually started a series of experiments that lasted over several years that culminated in an experiment involving a 1,600-pound draft horse, which died of natural causes, I assure you. But I then butchered it with stone tools and bone tools that I made all in an act of replicating some of the techniques that we were interpreting, that we were reconstructing from the fossil record. And here a colleague and I are introducing one of the legs of the horse through a hole in the ice to be stored in this pond. And here is a mass of meat from the horse just a few weeks later. Here a few months later, there it is. And the short of it is that it really was quite well preserved. There is a bacterially mediated transformation that results in a different smell and taste to the meat after it's spent a whole winter in the pond. The last I ate off that meat was on July 4th at a barbecue. And by that time it was pretty strong, but it was just fine in terms of health concerns. So this does really work. This meat caching does really work. All right. Now I have to come back to tusks. And again, time is my enemy, so let me try to take you through a little bit of what kind of information we can get out of tusks. In the first place, here's a mastodon tusk. I've cut off the tip, so that's a transverse cut perpendicular to the long axis of the tusk. This portion of the tusk, however, has been cut longitudinally, and so you're seeing that cut more like you would cut a board out of a tree. In the cross section, you see these concentric zones, dark and light zones, look like tree rings, and in fact, those are going to represent years in the animal's life. Here on the board surface, as it were, you also see the same dark light zones, and it's a little trickier to follow because it turns out they're long, narrow cones on that view. Now, in order to give a better sense of the three dimensions of this and how it develops, this is a mammoth or a mastodon tusk stripped of an outer layer called cementum. So this is really the inner mass of the tusk, but this is what makes up 90% of the mass of the tusk. Obviously, they aren't colored like this in real life, but those colors are meant to indicate time. They are a key to time in this diagram. Each cycle of each rainbow cycle is 1 year in the animal's life, and you can think of the first colors, which are going to be the reds, as being January, and the next colors February, March, and so on. And this is the last frame of an animation, but to orient you, the tip, the base, there's a conical pulp cavity here occupied by soft tissue. It's soft tissue inside that pulp cavity that forms the conical layers that accrete, that build up, that make the structure of the tusk, that essentially write the record of the animal's life. And here then is the animation, seen as if you were sort of a fly on the forehead of the mammoth, but we're only looking at one tusk here. So think in terms of the tip being, you saw it at the beginning, it's the early years of life. And the base, those are the late years of life. And in fact, the surface of the pulp cavity, that's the day of the animal's death. Now, here is a tusk that's cut, so you see the cones, and what you're seeing building up here is a stack of cones, starting with the red, ending with the purple, and by the time you look at it in cross-section, notice that in contrast to tree rings, time goes from the outside in, not from the inside out. The first one, the red, is on the outside, the purple one is on the inside, in a local cut across the tusk. In order to get the whole life story, you therefore have to look from the tip to the base, either in a longitudinal section or by taking a series of samples that collectively sample a bunch of sites along the length of the tusk. So they're not trivial to sample or to study. Now I get these samples in one way to get them is by cutting tusks longitudinally. Well, how do you do that? Well, with a bandsaw to start with. Tusks are curved, so this is actually quite a complicated operation. The tusk is suspended here from a large number of nylon cords. I have a rolling scaffold made from plumbing supplies, basically, and this scaffold rolls by my bandsaw, and you get the sort of idea of the dance that the tusk has to do to go completely through the cut. Again, I'll rush this along a little bit. We did it, I used to do it freehand like you see on the left here. I now tend to do it with a little more control by making what I call a rocker box here. and the tusk is mounted in the rocker box with polyurethane foam. So this is an elephant tusk actually in here, but I've done this with mammoths and mastodons as well. And so I'm just starting the cut right there. In this case, the zoo wanted the tusk back. They were only willing to give me a slice. So I said I can do everything I need to do with a 1 centimeter slice out of the middle. They said fine. So after making the first cut, I mounted the half tusk in the box again, started the cut, finished the cut. Did it work? Well, you might say, would he have shown us if it didn't work? Here I'm holding the slice that was removed, and here, yep, it worked. That's a 1 centimeter thick slice of an elephant tusk. And that's the sort of sample that we can analyze to get our information. Now, there's lots of ways to look at tusks. And just to show you one, here is a tusk irradiated with ultraviolet light. And it turns out that different parts of the annual cycle fluoresce differentially and produces this pattern of cones. You see, not so different from the diagrams that I showed you before. Now, I mentioned that you can also drill samples, and here we are with a heavy-duty drill and special homebrew coring bits with which we remove a solid cylinder of ivory from about a dozen positions along the length of a tusk. And having done that, you can then cut them, slice and dice them in various ways, and finally here on the right are 2 microscope slides with thin bits of ivory which we can analyze under the microscope and look at to see the record of those years in the animal's life. Now, I've already given you the idea that there are years there, and you saw the colored layers that I said were months, but I suppose you assumed that that was just for sort of a mental model. Well, it turns out it's more than that. Within the years of these animals' lives, there are much finer increments. And in mammoths, there are, for instance, weekly increments. And at a still finer scale, there are daily increments. In other words, we all have, you've probably heard of them, circadian rhythms, metabolic cycles. Our physiologies respond on a 24-hour cues. And within even our teeth, but certainly in the tusks and molars of a mastodon or mammoth, there's a daily rhythm of deposition of material leading to structural features that we can see under a microscope. 1 day, a second day, a third day. And these larger units that you see here are then in mastodons, actually 2-week periods. In mammoths, they're week periods. We'll fuzz over that for the moment. But it means that these tusks really are diaries in the most direct sense. Now, just to show you another way we can do this, this is using a microCT, CT scans. Maybe some of you had CT scans, computed tomography. MicroCT is just a miniaturization of that to get even higher resolution, better structural detail. And this happens to be a chin tusk of a mastodon. They had chin tusks as well. And these bands of where you see density gradients here, remember in an X-ray-like image, the light part of the image is the dense part, the darker part is the less dense part, and these density gradients here represent individual years of the animal's life, formed in this way, with this being the time of death. Okay, this is a summary slide where I'm trying to indicate the number of things, the range of things that we can extract from tusks, the kinds of data. The organization of this is that here's a variety of structural features, measurements of thickness and length and counts of increments, and here are compositional features. These are mostly measurements of ratios of different isotopes of particular elements, and I don't suppose many of you are into isotope geochemistry, but let me just say that any given element like carbon or nitrogen or oxygen comes in different varieties where the atom is of slightly different masses. And it turns out that we can learn a lot about physiological processes by looking at the ratio of the two different, or two or more different isotopes of a given element. And without explaining all the details, let me say, for instance, that by looking at nitrogen isotopes from collagen, which is the organic material in tusks or teeth, we can learn whether that animal was in nutritional stress or not, whether he was well fed or not at that point in its life. This is not something only about the end of life, it's about the whole life. You know, give me a whole tusk, I'll sample it from season to season, from year to year, and tell you the history of that animal's dietary quality. There's data about the animal's reproductive lives, when they became sexually mature, when females had calves, what time of the year they had calves, what time of the year they died. There's also information about environments here, and given the lateness of the hour, I'd better leave it there, but there is much more. We'll have one more example that I'll try to blow quickly by. We're going to look quickly here at the life of one male mastodon. This is a cross-section of its tusk near its tip. There's the center. There are concentric years. You remember, the first are on the outside, the subsequent ones are on the inside. This isn't the end of life, though. It's only the last year encountered in that particular cross-section. Here is the part of the tusk that we cut longitudinally, a sample here, a sample there. We cut the samples so that there's some overlap in our access to particular years, and collectively we then put together a picture of the whole life. And here are 11 different samples, some of them with as many as a dozen or so years in them. There's a lot of work that goes into looking at here just 32 complete years, but it's a very detailed record of life. Since again I'm under pressure of time, this is one way of summarizing some of the information. This is the thickness of these fortnightly increments. Think of this as a sort of musical score, the comings and goings, the good times, the bad times in the life of this animal. For most parts of life, there is a clear annual cycle, and the thicker increments, guess what, are in the summer. The thinner increments, guess what, are in the winter. There are good times, there are bad times. Here's a particularly bad time. What happened there? That's when this male became sexually mature, was evicted as a young calf from the matriarchal family unit in which it had grown up. It was the worst year of his life. But he did survive, and actually got to where he was doing pretty well. And then something else happens in here. It's indicated by these little M's, which I'm going to now circle. Something was happening each year in the early summer. What was it? It was a slowing of growth, and it turns out we'll see there's evidence of something bad happening to its tusk. Well, not too bad, but a minor injury. Turns out that was must. Must in elephants is like the rutting season. It's a time when they go on a fast, when they think of nothing else but you know what. And they get in fights sometimes over it. And one of those fights is illustrated here. This isn't just a pure fabrication. Elephants do it, but again, we've got fossil evidence that shows that mastodons did it. Now, what kind of fossil evidence? Well, one of the kinds of evidence is that we've got holes in the sides of skulls that really can only have been made by this sort of a movement. And I've done animations with our 3D models. See, they're coming in to help us really here figure out what was going on. But there is, in addition to that, a physical record. We're looking here at a cast, actually, of a tusk, and there's a series of ridges, strange, funny, gnarly parts of the tusk surface. They're of different lengths, but they're all centered on one transect through here, which is along the outside curve of the tusk. No time to take you through too much of that. I will note that they come always at the same, sort of in the same relative position relative to a sort of undulating surface of the tusk. And when we reconstruct the seasons of the year, those undulating surfaces are undulating on an annual cycle. The seasons of the year, spring, summer, fall, winter, spring, summer, fall, winter, these lines come about in the early summer. So it's always at the same time of year. And this is now an animation that shows how those form. And you watch this tusk go down, and you notice how the base is then driven into the back of the socket. And so what we're seeing is the evidence of a barroom brawl, really, that this animal got into. It fought it's an opponent with an uppercut using its tusk. The tusk was driven downward by the reaction force, was driven into the back of the socket. It produced a little crimping of the cells that produced the cementum at just that position, and they produced gnarly cementum ever after. And thus the tusk holds a record of every fight that animal was in. And that's how we know about the details of that animal's reproductive life. We come here to Luba, and I'm coming in almost for a landing, but we're still in the air, so hang in there with me a bit. Luba is this, remember, spectacular woolly mammoth found in northwestern Siberia. Here, I almost feel like she's going to step right off this edge of the stage. We're looking up close at her. Here's just the little nub of what turns out to be her milk tusk. Not even the permanent tusk yet. This was her milk tusk, the precursor of the permanent tusk, and it still hadn't broken the skin. It's still covered by a nub of skin right there. But we studied her in great detail. This was the first of 2 dissections. We removed the teeth from one side of her face here, the left side. We're also here opening an incision into her abdominal region where we removed some of her intestinal contents. And I'm remarking here to my colleagues, look at this, what's inside here. It turns out, here's a baby that by all rights should have been eating only her mother's milk, and in a moment you'll see that she was. But in addition, we're finding grass in her intestinal tract, grass that has been sheared by nothing other than adult mammoth teeth. And it'll take me a couple slides to put this whole picture together, but hold that in your mind. First of all, as I said, she's a young calf. It turns out she was a month old at death. These are the remains. We've analyzed these by all sorts of wet chemistry and infrared spectroscopy. These are basically the partly digested remains of milk. So mother's milk is still there in her intestinal tract. But in addition, in her intestinal tract are these bits of grass that are here on their ends, sheared off like that one is, all at this sort of standard length. And that length is the spacing between the enamel ridges on an adult mammoth's tooth. Now, what's going on here? Luba's teeth weren't even well enough developed to chew grass like this. So this was instantly evidence that somehow what an adult mammoth ate got into Luba. And the short of this is that Luba's mother was feeding her fecal material. Aghast. Turns out elephants do it. Lots of animals do it. It's how many herbivores inoculate the intestinal tract of the young with the bacteria that form crucial roles in the digestive physiology of these animals. They couldn't digest the cellulose that makes up a great deal of their food without those bacteria, and that's how they get them. And so Luba's mother was doing it, and this was the first evidence that mammoths did it. Now, let me also say, just in passing, and I'm going to leave this, maybe, and we can come back to it in questions. Also in this intestinal material, we found one small bone of a lemming, well, not actually a vole, another small rodent like a lemming, and we found some hair. Now, you think about what that might mean. These are some of Luba's teeth. I really don't have time to tell you much. They do, on their roots, have these little constrictions that it turns out represent the moment of Luba's birth. The smaller teeth that were on the left, we cut. I know that from your distance you can't see very much, but there is a strong line that lines up with these constrictions at the base of the root, and the dentin that was formed before that line is very different from the dentin that formed after it. Turns out that is a neonatal line. We have here approximately 18 months of Luba's development in utero recorded in those teeth, and then her birth, and then 30 days of her short life after birth. And so it's really remarkable detail that we're getting. And again, I can't take you through all the steps. This is one of those slightly larger teeth. This is from a microCT analysis of the tooth, and it looks delicate down here toward the base. It is. That's the actively growing margin of the tooth, and so you're seeing something here that it's almost unimaginable without some of these techniques. I better blow by this pretty quickly. How would you ever document such a thing and make it so that your colleagues could see it? Well, in fact, we can. We have to just sometimes fiddle a little bit with the digital data, thicken some of those very thin surfaces, and then using a 3D printer, which is another new technology, we can make a physical model, whereas you would never be able to make a mold or cast of those teeth. They're so complex and interwoven. So lots of opportunities presented by some of the new technology. We also CT scanned Luba's whole body. You're seeing her dance here before you and gradually become transparent. There's her appendicular skeleton, and now it's becoming transparent. And what's that green? It turns out it's a mineral, an iron phosphate, vivianite, that's present in her long bones. And there's a whole story about her death and the physiology of really the last moments of her life. And again, I can't really go into it, but let's bring her bones back to normal sort of opacity here. And so there you see them. You can see that parts are denser and parts are less dense. If we color code that, there you can really see it. The yellow is the part that's more fully ossified. The blue is what's still cartilage. We've got the whole developmental history of the animal skeletal development. So there's a great deal we can tell about individual development. This is a foot sort of spinning here. And again, only those little yellow nubs